Hello, welcome to our coffee and conversation with EAG expert proceeding. Thank you for coming to this event, and we hope that you are going to spend valuable time with us today. We start today's meeting with a brief introduction to Eurofins EAG laboratories, followed by presenting slides about our purity survey techniques and methods. After that, we discuss some of our techniques' strengths and limitations by using examples from typical case studies. Optional is a tour and demonstration of the analytical tools which we use to provide measurements on a contract basis. Eurofins EAG Material Science is a global scientific contract services company. The first EAG facility and business unit was originally established in Mountain View, California in 1978. This EAG has over 45 years of experience in material testing services. With 20+ facilities located in the US, Europe, and Asia, and 5 business development locations in over 20 countries, we serve more than 5,000 clients worldwide. Our 1,000+ highly educated and skilled employees, combined with over 2,000 industry-leading, state-of-the-art analytical instrumentations and accessories, enable us to leverage the power of science and engineering to accelerate innovations, developments, and manufacturing through creative problem-solving, objective analysis, and expert interpretation of measured data. We are IP secure and ITAR registered. Although we are a global company, we are following strictly US export control regulations. We are accredited and certified across multiple industries and markets. We have a business continuity plan that includes a global footprint with disaster preparedness and worldwide redundancy. EAG was acquired by Eurofins in 2017. Our parent company is a multi-billion-dollar global leader in testing for life scientific services with a portfolio over 200,000 validated analytical methods. In this world map, laboratory locations of facilities are illustrated with orange dots, and sales and business development locations are presented with blue dots. The largest number of EAG laboratories are located in California, mainly in Silicon Valley, where the company was originally founded. But we are also present in the Midwest in St. Louis, Missouri, and 3 locations on the East Coast, Syracuse, New York, Princeton, New Jersey, and Raleigh, North Carolina. We have laboratories in multiple countries in Europe, such as Toulouse, France, Eindhoven in the Netherlands, and 3 locations in Switzerland. In Southeast Asia, we have installations in Japan, Taiwan, South Korea, and China. All these contract service facilities are supported by commercial offices that are also present globally and as far as Sydney, Australia. We are best known for that we are providing services for a very diverse range of industries. Most importantly, the semiconductor device manufacturing industries, semi-equipment developers and producers, and consumer electronics industries. These are mainly supported by our California and Southeast Asia locations. But we are also known in the aerospace and defense, automotive, medical devices, high purity chemicals, telecom and data storage, energy, pharma, and a supply chain of raw materials. We also have a team of specialists. They are fully equipped to support almost any litigation case. EAG uses multidisciplinary analytical expertise, including the techniques that are here at Purity Survey Services, to provide support for full product lifecycle, including innovation and improvement, investigation and troubleshooting, quality control and assurance, manufacturing support, failure analysis, regulatory compliance, supply chain QA/QC, consultation, and litigations. Let's take a look at our smart chart. Smart chart is an acronym for spectroscopy, microscopy, analytical resolution tool, and it shows the family of techniques we have at EAG. This smart chart allows us to compare the spot size and sensitivity of each technique. The techniques are color-coded according to the descriptions at the lower left. For example, dark blue areas provide elemental information primarily, while green shows imaging information. The x-axis shows the range of spot sizes from 1 centimeter at the right down to 1 angstrom at the far left. Y-axis shows concentrations either in atoms per cubic centimeter at the left or at atomic concentrations at the right that range from 100% at the top down to 10 parts per trillion at the bottom. So with the box, you can select your technique based on the detection limit you need and the size of your areas of interest. Outside of the box are techniques that don't quite belong in the chart. The techniques on the right, for example, don't necessarily have a spot size associated with them. They are basically bulk compositional techniques that may consume your entire sample, and they have the detection range shown from the top to bottom. The techniques at the bottom are basically imaging techniques and don't provide composition per se, but they do have relevance with respect to the spot size on the x-axis. Let's look at the high purity materials techniques for advanced technologies. Let's look at the advanced technologies. High purity serves very broad industry sectors associated with advanced technologies because all these would not be able to innovate and manufacture products without high purity materials. In these technologies, trace and ultra-trace level elements intentionally introduced or unintentionally present could play a major role in the performance or life cycle of products made of. There is a compelling need to understand a material leading to the information versus the data paradigm. During this presentation, I will demonstrate how very sensitive full surveying analytic techniques are quite often indispensable for advanced technologies. Let's see the photovoltaic or solar materials. There are like a broad range of elements or materials they are used, either as the base materials or intentionally added. And then techniques, they have to have sensitivity to accurately determine the concentrations or relationship by depth or laterally in order the photovoltaic solar cells to function properly. Fuel cells and batteries is very different range of materials are used to produce fuel cells and batteries. And then we can go like spotter targets, the LED and phosphors. High performance ceramics. Aircraft engines in the aerospace industry. Electronic materials. Medical devices. Integrated circuits. All of these. And we can name many other ones, almost impossible to produce nowadays without high purity source materials. Now, if you look at the periodic table, advanced technologies utilize elements and isotopes practically from the entire periodic table to manufacture products that we use in our daily life. We often use during testing advanced materials that one man trash is another man treasure. For example, high mobility alkali and alkaline earth elements serve as mobile cations in advanced batteries, but they have very deleterious effects in the semiconductor or even photovoltaic-based composite materials or layered materials. Refractory metals serving as solution strengtheners in high temperature superalloys, but they're unwanted even at trace levels in electrolyte solutions. sulfur, selenium, tellurium can form 2D semiconductors similar to graphene with weak forces between layers. However, these impurities in superalloys weaken the mechanical strength of these alloys at high temperatures working conditions. Now, why purity matters? Here is one example, what trace and ultra trace elements, can affect the nuclear graphite. The oxidation resistivity and mechanical properties of materials at high temperatures, such as nuclear grade graphite, can be significantly affected even at very low trace and or ultra trace levels. Full survey analysis is essential for accurate certifications of these types of materials. DMS is one of the most effective analytical techniques for full survey analysis of solid carbon-based materials because besides hydrogen, it can cover the entire periodic table, including the gas-forming elements. Here is an example, the most frequently used nuclear-grade graphite, the NGV18. Most of the elements that are present and measurable, they are all at trace or ultra trace levels, which means the analytical technique can actually certify these materials, needs to have the sensitivity to actually determine and quantify these elements at this level. For that purpose, low discharge mass spectrometry is a technique of choice because it can analyze these carbon-based nuclear-grade materials in a solid state. Doping in semiconductors is a fundamental process that plays a crucial role in shaping the properties and performance of these materials. It refers to the intentional introduction of foreign elements into the semiconductor material to alter its electrical properties and conductivity. This process plays a crucial role in the design and manufacturing of various electronic devices and integrated circuits. The introduction of specific impurities, such as dopants, like phosphorus or boron, allows the manipulation of the semiconductor's conductivity. This manipulation can make the semiconductor either N-type or P-type. This alteration of conductivity is crucial for the operation of diodes, transistors, and other semiconductor devices. It enables precise control of charge carriers within the material, influencing its overall electronic behavior and performance. Doping profoundly influences the properties of semiconductors by modifying their band structure, charge carrier densities, and crystal lattice characteristics. Evaluating doping levels and the overall purity of the semiconductor-based material is essential for producing reliable electronic devices. Photovoltaic cells have multi-layered structures. One of the most frequently used PV technology is based on multicrystalline silicon. Control of metal impurities in multicrystalline silicon for solar cells is essential for manufacture for developing and producing the most efficient products based on MC silicon. Besides high sensitivity, since ultra trace layers of foreign elements can affect the minority carrier life in PV cells, analytical techniques are needed that provide also information about lateral and depth distributions of foreign elements in these type of multi-layered films. Modulated GDMS operated in microsecond pulse DC modes can achieve gentle sputtering rate in tens of nanometer depth steps, surveying up to 25 elements simultaneously with sampling orifice sizes between 4 to 8 millimeters. This example is a clear illustration of the battery electrodes that the performance of the battery that contains significantly higher foreign elements in this electrode loses capacity significantly faster than the battery that was produced using higher purity electrode materials. Superalloys are nickel, cobalt, and iron-based alloys containing many alloying elements that have various impacts in these alloys, such as mechanical strengtheners, thermal oxidation and corrosion resistance, long-term stability, especially at high temperature, foreign unintentionally present elements can be also present. Each alloying element is potential source of these foreign elements. Here is an example that some of these foreign elements present in these high temperature alloys, they have damaging effect on their mechanical strength at high temperature. For instance, bismuth, even at 0.2 ppm level, which is 0.2 microgram per gram, can cause creep ductility loss by at least 20%, while silver and tin has very little effect. Some important aspects between materials engineering, as the examples above illustrated, that purity, some impurities are known that they have deleterious damaging effect. Some impurities are intentionally added because they are beneficial for the life cycle or even the basic characteristics these materials are produced. But the roles of many impurities are less known. Besides, the materials generally produced with a certain composition. The composition uniformity is also very important. But the role of minor elements and minor phases are generally measurable with multiple techniques, and then part of the quality control and quality assurance process. But the relationship between purity and performance, like lifetime, reliability, and safety, requires highly sophisticated and very sensitive analytical techniques. Control doping and contamination-free manufacturing are essential to advance materials performance, reliability, and life cycle. Now, why full survey analysis? The examples again above illustrated that full survey is essential to have information about the material. In every step, the material is actually produced, used, and recycled. Residuals from raw materials to source minerals can be introduced unintentionally. Impurities can be introduced during manufacturing. Contaminations are introduced also during service, and segregation-induced impurity enrichment at the surface layer can happen during manufacturing or using the material. Now, why we are here to demonstrate how to select an analytical technique to provide the most complex and most comprehensive information about the material, either when devices are produced or used. First, the very important information is needed: what kind of impurities are present, and what the amount, what the location and distribution. These are the main steps selecting the right analytical technique for the full and comprehensive characterization of the material. Here in this chart, like this one, we demonstrate that we have multiple solid sampling analytic techniques that have different sampling depth. This useful chart shows the depth of analysis of each technique. For instance, time-of-flight SIMS has a very shallow sampling depth of only a few nanometers. XPS and OJ analysis depths are 10 nanometers. These surface analysis techniques are up to 3 orders shallower than another common and routinely used analytical techniques, such as FTIR or SEM-EDS. This means that surface contaminants or foreign elements in very thin films can be detected on samples by time-of-flight SIMS, XPS, or OJ, but most likely will be missed by other analytical techniques. The arrows indicate the deeper depths are available in some techniques by depth profiling modes or depth distribution analysis. Then why choose EAG? We are very strict in client confidentiality, which is core to our business. We are established through leaders in investigative science. We have an extensive knowledge base and skilled expertise. We can offer a multidisciplinary approach to support you. We can scale with your demand and meet your time constraints. We own more than 2,500 instruments worldwide. We are the global leader for materials testing services. And most importantly, we know how to solve materials and engineering-related product problems. And thank you for your attention.